In October 2025, two trains were traveling in opposite directions on a high-speed rail line in central China. When they passed each other, the combined speed of the two trains measured 556 miles per hour. That's faster than most commercial airplanes cruise at altitude. Each of those trains was the CR450, China's next-generation bullet train, currently in pre-service trials on the Shanghai, Chongqing, Chengdu line. And during those trials, a single CR450 hit 281 miles per hour, a new world record for any wheel-on-rail passenger train in history. For context, the fastest train in the United States, Amtrak's Acela on the Northeast Corridor, reaches 150 miles per hour on its best stretch and averages between 70 and 80 miles per hour for the full trip from Washington to Boston. And the Acela isn't even officially classified as high-speed rail. The CR450's commercial operating speed, the speed at which paying passengers will ride it starting in 2026, is 249 miles per hour. That's faster than the Acela's absolute maximum. It's the train's everyday cruising speed. China has 31,000 miles of high-speed rail in operation. The United States has zero. Not one dedicated high-speed rail line anywhere in the country. And China is about to make that gap even wider. In this video, we're going to break down exactly how the CR450 works, the engineering decisions that let a 694-foot-long train made of metal travel at nearly the speed of a small aircraft without leaving the ground on a standard railroad gauge. We're going to explain why the US is so far behind and what it would take to close that gap. And we're going to show you what the CR450 means for China's economic and geopolitical ambitions over the next 25 years.
To understand why the CR450 matters, you need to understand what high-speed rail does for a country, not just as transportation, but as economic infrastructure. High-speed rail doesn't just move people faster, it restructures geography. When a city that used to be a 4-hour drive becomes a 90-minute train ride, it effectively becomes a suburb of the nearest major metro area. Property values rise, businesses relocate, new economic zones emerge. China understood this earlier and more completely than any other country on Earth. In 2008, China had 0 miles of high-speed rail. The country launched its first line, connecting Beijing to Tianjin in time for the Summer Olympics, mostly as a demonstration of national capability. By 2025, that number had grown to 31,000 miles, more than 70% of all the high-speed rail track on the planet. Japan, which pioneered the technology in 1964, has about 1,900 miles. France has roughly 1,700 miles. Germany has about 900 miles. The United States, the world's largest economy, has 0. China didn't just build a rail network. It built a new economic backbone for a country the size of the continental United States, connecting cities that were previously isolated by distance or terrain. Today, 10,000 bullet trains carry 16 million passengers every single day across China's network. By the end of 2024, Chinese high-speed trains had transported a cumulative 22.9 billion passengers, a number so large it's difficult to visualize. That's roughly 3 times the world's entire population, every single one of them riding a high-speed train.
The network has reduced average travel time between China's 31 provincial capitals by nearly 50% compared to 2012. Cities that required an overnight train or a connecting flight are now a morning trip. And the economic impact has been documented in detail. Every major high-speed rail corridor in China triggered measurable increases in GDP along its route, higher property values, new industrial zones, and regional labor market integration. Now, China wants to go faster. The CR400, the current generation of bullet train, operates at 217 miles per hour. For most of the world, that would be an unachievable benchmark. For China, it was the starting point. The CR450 represents 5 years of engineering work by thousands of researchers, engineers, and manufacturers to push that number to 249 miles per hour in regular commercial service, with a tested ceiling of 281 miles per hour. And the system has been designed to require no new track infrastructure. the CR450 runs on the same rails China already built. You don't need a new network to deploy the fastest train on Earth. Why couldn't the US do what China did? The honest answer involves history, politics, and geography. But ultimately, it comes down to choices.
The US once had a serious passenger rail network. In the early 20th century, trains connected American cities efficiently and reliably. Then came the interstate highway system, followed by the expansion of commercial aviation and the systematic lobbying of automobile and airline industries against passenger rail investment. By the time the rest of the world began building high-speed rail in the 1960s and 70s, American political consensus had already decided the country's future was cars and planes. Today, the cost to build a true high-speed rail network across the United States from scratch, the dedicated track, the tunnels, the bridges, the grade separations, would cost an estimated $4 trillion, according to the Cato Institute. The 2021 Infrastructure Investment and Jobs Act allocated $66 billion for all rail projects combined. That's less than 2% of what a real HSR network would require. Meanwhile, in the Northeast Corridor, the single most traveled rail route in the country, trains still slow to 30 miles per hour in places because they run on track built during the era of Reconstruction, after the Civil War. Not upgraded since the Civil War, built during it. China, starting from nothing in 2008, built more high-speed rail in 17 years than the entire rest of the world combined. The US, in the same 17 years, spent most of its time debating whether to fund the study.
So how do you build a train that travels at 281 miles per hour on steel wheels on steel rails without shaking itself apart? The answer is that you have to fight physics on multiple fronts simultaneously, and the CR450 represents the most comprehensive solution to those physics problems ever built into a passenger train. The enemy: air. At 150 miles per hour, aerodynamic drag is a manageable engineering challenge. At 249 miles per hour, it becomes the single most dominant force acting on the train. Drag increases with the square of speed, meaning if you double the speed, the drag doesn't double, it quadruples. Going from 150 to 250 miles per hour doesn't double the air resistance problem. It makes it nearly 3 times worse. The nose of a high-speed train is the most critical aerodynamic element. When a train pushes through the air at 249 miles per hour, the air has to get out of the way. If the nose is too blunt, the air stacks up in front of the train and creates a massive pressure wave, which wastes energy, causes vibration, and at high enough speeds, creates a sonic boom-like effect that can damage structures near the tracks and disturb passengers in tunnels.
The CR400, the previous generation, had a nose cone measuring about 41 feet long. Engineers spent 5 years studying how to improve on that. The CR450 has a nose cone measuring 49 feet, nearly 8 feet longer, sharper, and more tapered. Combined with redesigned undercarriage panels and fully enclosed bogies, the wheel assemblies underneath the train, the CR450 achieves a 22% reduction in aerodynamic drag compared to its predecessor. A 22% drag reduction doesn't sound dramatic until you understand the math. In high-speed rail, a 1% improvement in aerodynamic drag takes years of engineering and testing to achieve. Getting 22% required a comprehensive redesign of nearly every external surface of the train. The weight problem. Physics also demands that a faster train be lighter, both to accelerate more efficiently and to reduce the forces on the track, which must handle the stress of a heavy vehicle traveling at extraordinary speed. The CR450 weighs 110,000 pounds less than the CR400 it replaces. To put that in perspective, that's roughly the weight of 7 fully loaded Greyhound buses that engineers removed from the train through the use of carbon fiber composites, magnesium alloys, and precision structural redesign. That weight reduction, combined with the drag reduction, gives the CR450 its acceleration profile. The train goes from a dead stop to 217 miles per hour, the speed the current CR400 cruises at commercially, in just 4 minutes and 40 seconds. The previous generation took over a minute longer to reach the same speed. A minute and 40 seconds faster from zero, at the very speeds where aerodynamic drag is exponentially fighting you every inch of the way. The track problem. Here's the engineering challenge that most coverage misses. The CR450 runs on the same track as the CR400. No special rail, no new infrastructure. The same standard gauge, 4 feet 8.5 inches between the rails, used by most rail systems on the planet. To make a train go 32 miles per hour faster on the same track while reducing the forces that track has to absorb, engineers had to redesign the bogie, the wheel assembly that connects the train to the rail. The CR450's bogies are fully enclosed in aerodynamic fairings, reducing the turbulence that used to churn around the exposed wheel assemblies at speed. The axle load, the weight each axle presses onto the track, is just 32,000 pounds per axle, roughly the same as its predecessor, despite the extreme speeds. The result is that the CR450 can operate on all 31,000 miles of existing high-speed track in China without modification. Every city already connected by HSR gets access to the world's fastest train without spending $1 on new infrastructure.
The noise problem. At 249 miles per hour, a train generates noise levels that can make it uncomfortable for passengers and disruptive for communities along the route. The CR450's interior noise target at full operating speed is 68 decibels, roughly the volume of a normal conversation. For reference, that's the same interior noise level the CR400 achieves at 217 miles per hour. China's engineers built a train that is 32 miles per hour faster and no louder inside the cabin. The safety problem. Speed means longer stopping distances. A car going 60 miles per hour takes about 200 feet to stop in an emergency. A train going 249 miles per hour, even with the best braking systems available, takes considerably more. The CR450's emergency braking distance at full operating speed is less than 4 miles. That sounds long, and it is, but it's within the safety parameters engineered into the track spacing and signal systems that control the network. The train also carries redundant systems. If one car's braking system fails, the others compensate. The entire train has to be certified through 373,000 miles of testing, the equivalent of circling the Earth nearly 15 times before a single paying passenger steps aboard. The tunnel problem. When a 281 mile per hour train enters a tunnel, something extraordinary happens. The train acts like a piston, compressing the air in front of it. At high speed, this creates a pressure wave that travels down the tunnel ahead of the train and explodes out the far end, a phenomenon called a sonic boom from a tunnel exit, or a micro-pressure wave. It can be loud enough to shatter windows in buildings near tunnel entrances. It can also cause a sudden pressure change inside the train that passengers feel as ear pain. The elongated nose cone of the CR450 is specifically designed to reduce the rate at which it compresses air when entering a tunnel, spreading the pressure buildup over a longer time and distance, eliminating the pressure spike at the tunnel exit. Japan spent decades solving this exact problem with its Shinkansen network. China solved it for a train going 30 miles per hour faster. 2 trains, 556 miles per hour. One final number worth sitting with. In the same test session where the CR450 hit 281 miles per hour, 2 CR450 trains passed each other traveling in opposite directions. Their combined speed at the moment of passing was 556 miles per hour. The air pressure event between 2 trains at that combined speed is so powerful that it can pull objects off platforms and flex the train bodies inward for a fraction of a second. The CR450 was engineered to withstand that force without structural deformation, without loss of stability, and without the passengers feeling more than a slight pressure shift. 556 miles per hour on a railroad track. China didn't build 31,000 miles of high-speed rail because it needed faster commutes.
It built them as the physical infrastructure of a specific geopolitical and economic strategy, and the CR450 is the latest and most powerful expression of that strategy. The domestic economy argument. China's geography is a challenge. The country has a coastline of roughly 9,000 miles, and its most economically dynamic cities, Shanghai, Shenzhen, Beijing, Guangzhou, are clustered on or near that coast. The interior, where hundreds of millions of Chinese citizens live, has historically been disconnected from the coastal economic engine. High-speed rail changes that equation. The Beijing-Shanghai route, one of China's busiest, currently takes about 4.5 hours. With the CR450 operating at 249 miles per hour, that trip falls to approximately 2.5 hours. Beijing to Shanghai becomes what New York to Washington feels like on a good day, a manageable business trip, not an overnight journey. When that happens, companies in Beijing can realistically draw from a labor market that includes Shanghai workers. Real estate markets in cities along the route change. New businesses cluster around station areas. Interior cities that were previously economically marginal become connected to the coastal economy.
This is documented, not theoretical. China's own data shows that average travel time between its 31 provincial capitals dropped by nearly 50% between 2012 and 2024, and transport revenue from rail is projected to exceed $137 billion in 2025. The infrastructure pays for itself through the economic activity it generates. The technology export argument. China's rail ambitions don't stop at its own borders. CRRC, China Railway Rolling Stock Corporation, the manufacturer of the CR450, is the world's largest rolling stock manufacturer by a wide margin. It supplies trains to countries across Asia, Africa, the Middle East, and increasingly Europe and Latin America. Every new record the CR450 sets, every headline about 281 miles per hour test runs, is a marketing document for Chinese rail technology exports. Countries that are building rail infrastructure for the first time look at those numbers and ask, who do we call? China has paired its technology with financing through mechanisms like the Belt and Road Initiative, offering not just the trains and the expertise, but the loans to build the lines. Rail infrastructure in Indonesia, Laos, Ethiopia, and across Southeast Asia has been built with Chinese technology, Chinese capital, and often Chinese workers. The CR450 represents the flagship of that technology portfolio. When a country is deciding whether to buy French TGV technology, Japanese Shinkansen systems, or Chinese HSR, and China just set a new world speed record, the sales conversation tilts.
The United States has made a series of quiet decisions over the past 70 years that add up to a clear outcome. The country has no high-speed rail, no near-term prospect of building any, and is watching a rival nation extend a structural infrastructure advantage that grows more significant every year. The U.S. rail investment in the 2021 infrastructure bill was $66 billion for all rail combined. China invests roughly that amount every single year, $107 billion in rail in 2023 alone. The U.S. figure for that same year was well under $10 billion in actual federal rail spending. The Brightline West Line, the first true high-speed rail project in American history, is under construction between Las Vegas and a suburb of Los Angeles, scheduled to open in 2028 at a top speed of 186 miles per hour. It's a 218-mile private line. China, in the same amount of time it will take the US to build 218 miles of rail between two cities that are essentially a straight, flat shot through desert, will have extended its network by several thousand miles and deployed a fleet of trains that go 63 miles per hour faster. California is building a line from Los Angeles to San Francisco, projected at a top speed of 220 miles per hour. Current projected cost, $128 billion. Projected opening, sometime between 2031 and 2033. The original budget was $33 billion. It has been in planning and construction for over a decade and covers a fraction of the distance China built in the same period.
The gap between American ambition and Chinese execution in rail is not a gap that can be closed by policy announcements. It is a gap that requires decades of sustained investment, political will, and institutional capacity that the US has not demonstrated it possesses. The bigger picture. High-speed rail seems like a domestic infrastructure question, but its implications extend beyond transportation. Every high-speed train China sells overseas is a point of influence, financial, technological, and diplomatic. Every record broken by a Chinese train strengthens the case for Chinese engineering standards becoming the global default. Every country that builds its rail network using Chinese technology, Chinese finance, and Chinese construction companies adds a layer of interdependence with Beijing. The CR450's 281 mile-per-hour record isn't just an engineering achievement. It's a statement about whose technology defines the future of mass transportation and whose doesn't.
In 2008, China had 0 miles of high-speed rail. By 2025, it had 31,000 miles, 70% of everything on Earth. By 2035, that number is projected to reach 44,000 miles. And now, China has a train that travels at 281 miles per hour, runs on the existing network without new track, weighs 110,000 pounds less than its predecessor, and is quieter inside at 249 miles per hour than the previous generation was at 217 miles per hour. The United States has 0 miles of dedicated high-speed rail. Its fastest train averages 70 to 80 miles per hour on a route that uses infrastructure from the Civil War era. Its first true HSR line, 218 miles through the Nevada desert, opens in 2028, if on schedule. China built a nationwide high-speed rail network larger than the rest of the world combined in the time it has taken the US to begin construction on a single private line between Las Vegas and Los Angeles.
That gap didn't happen because of some natural geographic or economic advantage China had. It happened because China made a choice to treat infrastructure as a national strategic priority and pursued it with the full industrial capacity of the state for 17 years without interruption. The CR450 is the latest product of that choice, and it will carry passengers at 249 miles per hour starting in 2026 on tracks that were already there, reducing the travel time between China's most important cities by up to 40%, while connecting interior cities to coastal economic centers that were previously out of reach. This is what a country looks like when it decides to build the future instead of debate it. Subscribe to World Shift and turn on notifications. Every week, we bring you the real story behind the numbers, the mega projects, the power shifts, and the engineering breakthroughs that are quietly redrawing the global map. Understanding what's coming starts today. We'll see you in the next one.